Hello everyone, my name is Subham Paul and I am a PhD student at the Department of Mathematics IIT Patna. This is a short tutorial on simplicial complexes and Euler characteristic. In 1736, Leonhard Euler wrote a paper called The Seven Bridges of Königsberg. In that paper, he dealt with the question that is it possible for a person to plan a walk in such a way that he will cross each of these bridges once but not more than once. So this is the pictorial representation of those seven bridges. What Euler noticed was that one could look at this geometric problem without the notion of distance. There are many extra informations like width and length of the bridges, etc., which have no role in finding the answer to this problem. The method Euler used was quite simple. He represented the situation as a graph. So this is the graph. So the graph is a collection of points and edges, and in particular, he make the land regions vertices, the bridges as edges, as you can see from this graph. He then proved that for a graph to have such a walk, there can be at most two vertices with odd number of edges touching them. But here you can see there are four vertices in this graph, and all of them has odd number of edges touching them. So therefore the question to this particular problem is no, this is not possible. So the walk is not possible. Not only that, Euler also noticed that any convex polyhedron, if you take, the number of vertices minus the number of edges plus number of faces is always equal to 2. For example, you can take this particular cube and you know the number of vertices is 8, number of edges is 12 and number of faces is 6. So therefore the quantity V minus E plus F is actually equal to 2. And the fascinating fact is that it holds for any convex polyhedron. Now, so to understand this fact deeply, we need to rigorously define what is meant by these vertices, edges, and faces. So far, what is this vertices, edges, or faces? These are all vague, not mathematically well defined. Now we'll proceed to rigorously define few objects, and then we'll be in a situation to formally define Euler characteristic. To do so, first we have to understand what is called abstract simplicial complex to be precise. Let V be any set of finite number of elements, and the set we will call this is the set of vertices. Those elements will be called the vertices. A simplicial complex capital K on V is a non-empty collection of subsets of that set V which satisfies two conditions. The conditions are that any small v in capital V, the set small v has to be in the collection, and number two, if sigma 1 belongs to K and sigma 2 is a subset of sigma 1, then sigma 2 also has to be inside K. The elements of a simplicial complex are called simplexes. So a simplicial complex is nothing but a collection of simplexes. And if you take any simplex in a simplicial complex, then we say that the dimension of the simplex is actually nothing but the number of elements in that simplex minus 1. Take particular example. Take this example. If we take the vertex set to be 1, 2, 3, and these are some collection of subsets of capital V, this K1 and K2, and one can easily check that these two subsets are actually indeed simplicial complexes. And if you take this singleton to 2, this is a seed 0 complex because it has one element, so 1 minus 1 as the dimension is 0. And similarly, this has two elements, 1, 2, the set containing 1, 2, so therefore this is the dimension of the simplex is 1, and we can also say one simplex in K2. Now, from the combinatorial data of a abstract simplicial complex, we'll construct something geometric. Okay, to understand which is actually called geometric realization of a abstract simplicial complex. To understand what is a geometric realization is, we first need to understand first we need to define what is called geometrically independent subset of Rn. A finite subset from A0 to Ak of points in Rn is called geometrically independent if the set A1 minus A0 to Ak minus A0 of vectors in Rn is linearly independent in Rn. So the definition is quite simple, and one can easily check that it is clear that no finite subset of Rn containing more than n plus 1 elements can be geometrically independent, simply because of the fact that no subset of Rn which has more than n elements can be a linearly independent set. So also the first observation is the definition is well defined. Why? Here you can see that it feels like the definition depends on the ordering of the elements, right? Because this set A1 minus A0 to AK minus A0 is actually dependent on the point A0. But one can easily verify that this is not the case. This definition is order independent, and that is it's a well defined. Now the next observation is in R2, a set of 3 points A0, A1, A2 in R2 will be geometrically independent if and only if they do not lie on same straight line, that is they are vertices of some triangle in R2. Similarly, a set A0, A1, A2 and A3 in R3 will be geometrically independent if they are vertices of some tetrahedron. When I'm saying tetrahedron, that is a non-degenerate tetrahedron obviously. Now we are in a situation to understand what is called a geometric realization of a abstract simplicial complex. So let K be a simplicial complex and phi from K0 to Rn be an injective mapping, where K0 is the set of all zero simplices or you can say the vertices. Then phi induces a geometric realization of K if phi of K0 is geometrically independent. The geometric relation of K with respect to phi is denoted by this symbol and is defined as defined as the union of this union of the convex hulls of phi of sigma for all sigma in K. Then phi is known to be an affine embedding. Now let's understand this definition with an example. Let us take this subset, finite set A0, A1, A2, and take this K1 to be a geometric a simplicial complex. Now take phi from V to R2 defined by this. You can easily check that phi is a injective mapping. Now these are the points 0, 0, 0, 1, 0 and 0, 1. These are the images of A0, A1 and A2 under the map phi. Now we can check. So what you have to do to understand, so this is we are trying to find this is in R2, find the geometric we're trying to find the geometric realization of this abstract simplicial complex in R2. And what is happening here? So this is phi of E0 of A1 and phi of A2, and therefore you can see now this A0, A1, A2, we have to take the simplicial we have to take the convex hull of phi of A0, phi of A1 and phi of A2. These are only these points only, and finally the convex hull of phi of A0 and phi of A1, that is actually this. So therefore this is actually geometric realization of the simplicial complex K1. Next, now we'll take another simplicial complex over the same vertex set K2, and here in this case you can see this hollow triangle will be our geometric realization. Similarly, in this particular case, when K3 is here, A0, A1, A2 are there. So if this is phi of A0, phi of A1 and phi of A2, and therefore as because A0, A1, A2 are there, we have to take the convex hull of phi of A0, phi of A2 and phi of A2, phi of A1 and phi of A2, and therefore this is the filled in triangle will be the geometric realization here. And in this particular case, suppose this is A0, this is A1, this is A2. One can check the geometric realization from this will be, and this is I think A3. So yeah, and obviously this will be filled in because A0, A1, A1, this is the two simplex is here. So you have to take them. Yeah, so this is the geometric realization of this particular simplicial complex K4. Now, given a simplicial complex K, we now understand what is a geometric realization. So, geometric realization of a abstract simplicial complex is nothing but under some affine map phi will be a subset of Rn. Now, we induce the subspace topology of Rn to make this geometric object a topological space. Now, the question is, what is the relationship between two different geometric realizations? So, if one abstract simplicial complex capital K is given, then there may be more than one affine embeddings. So the answer is that the topology of the geometric realization does not depend on the particular affine embedding. That is what I am trying to say is that means if K is given to be a abstract simplicial complex and these are two affine embeddings, then with respect to the geometric relations of capital K with respect to phi1 and phi2 will be homeomorphic. So if only the homeomorphism we only if the only homeomorphism we only care about, then there is no difference. Now we are in a situation to define what is called a Euler characteristic. Given a simplicial complex capital K, the Euler characteristic of capital K is defined to be chi of k from summation from I from 0 to dimension k minus 1 to the power I multiplied by the number of I simplices, where dimension of k is nothing but maximum of dimension of all sigmas, where sigma is are simplexes in capital K. So for some examples, for this hollow triangle, you can see there are only three 0 simplices and 3 1 simplices. So therefore 3 minus 3, the Euler characteristic is 0. And for this filled-in triangle, similarly 3 0 simplex, 3 1 simplex, and 1 2 simplex. Therefore the Euler characteristic is 1. Now Euler characteristic is homotopy invariant. That is, if K and L are two simplicial complex such that the geometric realization of K is homotopy equivalent to geometric realization of L with respect to any affine embedding, because they are all homeomorphic, then the Euler characteristic of K will be equal to Euler characteristic of L. And therefore it is a topological invariant, as homeomorphic spaces are obviously homotopy equivalent. But there is a warning. Euler characteristic is not a perfect invariant. Here you can see two examples. Here you see one example that these are two geometric realizations of two simplicial of some simplicial complexes, and they are obviously not homeomorphic to each other. But you can see their Euler characteristic are same 0. And now finally, we'll talk about Euler characteristic and Riemann hypothesis. This is very interesting result, I will say. This is due to A. Bjorner is from the paper A Cell Complex in Number Theory. So first we construct a set called the set capital S, the set of all natural numbers. No, sorry, the set of all square free natural numbers greater or equal to 2. That is, all those natural numbers greater or equal to 2 which are not divisible by any prime square. And the set will be this, like 2, 3, 5, 6, 7, 11. So 15 is not 15 will be also be there, but you can see 16 will be not here because it is 2 to the power 4, and so 2 square divides 16, so 16 will not be in capital S. Now for all n greater or equals to 2, let Kn be the simplicial complex on the vertex set Vn, the set of all small s in capital S, such that S is less equal to n. And the K simplex in capital Kn is the least of this form, that S0 divides S1 and S1 divides S2 and Sk minus 1 divides Sk. And these Si, where these Si are all small si are all members of capital S. So you can see the K2 will be only one element will be there, that is 2. That is similarly K3 only 2 and 3, and there will be no 1 simplex because 2 doesn't divide 3. Similarly K4 there will be only again 2 and 3. Again there 2 doesn't divide 3. Similarly K5 there will be 2, 3 and 5 because these are the members less equal to 5 in capital S, and there will be no 1 simplex because none of them divide each other. Similarly now, but the K6 will be interesting because there will be 4 0 simplex, that is 2, 3, 5 and 6, and you can see 2 divides 6 and 3 divides 6, so there will be 2 1 simplexes. So this is the geometric relation of the K6. And similarly you can go on K7, K8 and so on. So this you get a sequence of simplicial complexes, and therefore you get a sequence of, I should say, in the set of integers. Now the deep result is that this limit involving the Euler characteristic, the sequence of Euler characteristic, is actually equivalent to Riemann hypothesis. That is, if you can prove that this limit is true for all epsilon positive, then you actually prove the Riemann hypothesis to be true. And that is, so therefore this seemingly innocent looking Euler characteristic has deep mystery surrounding it. Okay, thank you so much.